Okay, we have come to the part where we will be doing the analysis. Previously, we have already discussed how to derive the differential equations, and then also after the differential equations, we're going to apply the solution. So based on if it's a first order or a second order differential equations. Now, this portion is where we're going to do the analysis with our with an example of our differential equation circuits. Okay. So this part here is a general solution for circuits with step response, but this also is a for all kinds, no? Not only for step response. And then we will be doing the initial conditions and then the analysis. Okay, so what we have here is a not so simple example, no? So that we can already incorporate all the analysis that we have, all the analysis in all the discussions that we have made. Okay, so let me make this bigger so that you can see it. Okay, let's read the problem. So at switch 0, the switch 1 right here, the switch 1 right here, no, is closed. And switch 2 is closed 4 seconds later. Okay, so the switch 2 is closed 4 seconds later. So this one is at time 0 right here. And then later, switch 2 is closed. Okay. So find I of t for t greater than 0 and calculate I for t is equal to 2 seconds and t is equal to 5 seconds. Okay. So first is to help you analyze with the circuit, we are going to create different timelines and also redraw the circuit. So at t equal to 0, t equal to, let's just say, let's have t, this one is in between 0, t is greater than 0, between 4 seconds and 0 time. Okay, so at time between 0 to 4 seconds, we will have this kind of circuit. We have 4 ohm. Okay, the switch is already closed, but switch 2 is not yet open. Okay. Let's put equal right. You have another resistor right here. That's 6, that's 4 and 6. 6 ohm, and then 1 inductor right here. That's 5 Henry. Okay, so the switch 2 is not yet closed, so we will consider it as non-existent pa siya no, at this moment. So there we have it. This is our circuit from 0 to 4 seconds. Now, usually what we do, in the previous example, we will have this one shorted, no? si inductor. But at this point, since we only have a very few time, 0 to 4 seconds, we will need to come up with a general equation for this. No? Usually, we will be shorting this one, si 5 ohm, say, diba? Usually, we'll be shorting this one and we'll just do 40 divided by 10 ohm. Then we will get 4 amps. Okay. So, si 4 amps, that should be the current flowing here at the 5 Henry inductor if we have a long time to charge it. No? If Yes, if there was a long time to energize the inductor, then surely inductor will behave as short and you will get 4 amps current. Okay, but at this moment, we only have 0 to 4 seconds, so we will need to find the general equation of the current in the inductor at between this time. Okay. So looking at this circuit, we should be able to uh, analyze that yes, this one is a RL circuit with a 40 volts source. Okay. So we have this, we will be using the general solution, no? General solution. Or the complete response na lang. Complete response. So complete response is that we have I of t is equal to I transient plus ISS. Okay. So actually, we will be using this one as our general solution. But coming to analyze that we are not going to arrive at a steady state. So it's okay, no? It's okay, we're not going to arrive at a steady state. But still, we will perform this solution. So I of t, we have a solution as AE let's just do the solution, this one, as T. So, but first, before we can apply the solution, we need to know the differential equation of our source-free RL circuit. So, source-free RL circuit, you have di over dt plus R over L I equal to 0. Okay, so this one, let's say that this is the solution for our transient. Okay, and this one is what we're going to apply. This is our transient na IT because this is the source free. Okay, this is our transient. And so we are going to apply this one, I of t, di of dt is equal to AS EST. So applying it into our differential equation, we have AS EST plus R over L AEST equal to 0. Factoring out AEST, we get S plus R over L equal to 0. It means S is equal to negative R over L. Now, applying it into our uh, general or the complete response, I of t is equal to A e to the negative R over L t plus I is S. Now we come up with our differential equation check, come up with our solution right here. And then we need to determine the values of our constants, which is A. And how about the ISS? Okay. The ISS is, you can pause now if you want to answer. But ISS will be the steady state supposed to be. Okay, supposed to be the steady state of this circuit, which is ISS is equal to 40 volts divided by 10 ohms. So we get 4 amps. Okay. This is supposed to be the steady state of this circuit if they have a longer period of time. No? So I of t, then okay, I of t is equal to A E negative R over L T plus 4 amps. Now we need to know the letter A here, no? So then we will be using initial conditions. Initial conditions. The initial condition is where we are able to get the value of our constant A. So initial conditions at I at 0 time. So do you know the I at 0 time? So this circuit happened I at 0 time, and we know that the inductor is resistant to current. So I at 0 time, we have an open circuit for our inductor, and that's 0. So wala siya initial, it was not initially energized. So, ano siya bali? Okay, now, next step is, so I at 0 time, that is equal to 0. You have A e to the negative R over L at 0 plus 4 amps. Okay. So, 0 is equal to A plus 4 amps. So, A is equal to negative 4. So, our complete response is equal to negative 4 e to the negative R over L t plus 4. So this is our complete response. So take note, class, if we're going to use the equation I of t is equal to I infinity plus I at 0 time minus I infinity e to the negative R over L t. So this is our complete response, right? So we have here 4. And then we have here as 0. We have here as 4 again, but we have negative, so that's negative 4. E to the, so we will achieve the same equation. So 4 minus, P4 minus 4 e to the negative r over LT. Okay, so they have exactly the same. Okay. So actually, this one is applicable. So this solution is applicable for source free and for step response. Okay. Now, coming back to the problem, so we have here as, so this is only true for, this answer is only true for a time 0 to 4 seconds. So this is our general equation to 4 seconds. Okay. So ato na siya butangan og time frame. Okay. Next, our next time frame will be at 4 seconds onwards. Okay. 4 seconds onwards. Let's copy this one again. I'll just be okay, we will redraw the circuit with a different time frame at t greater than or equal to 4 seconds. So now we have the 10 volts added into our circuit. Forty volts, 10 volts, 2, 4, 6, and 5 Henry. So this is our equation, no, our circuit for a time 4 seconds. Okay, so let's do the now we will be doing again the same general solution. Okay, same general solution, which is I of t is equal to a e to the negative r over l t plus ISS. Okay? Same lagi hapon. Okay? But with a different initial conditions. Okay, different initial conditions. Let's do t greater than 4 seconds. So that we can differentiate them. I add a at greater than 4 seconds. Okay, so how should we do this one? First is we will need to determine what is the steady state na lang sa ta, okay? What is the steady state condition of our eye right here? Okay. So since steady state naman ta, wala naman tayo kanang other switching actions. So we will have we can be sure na after a very long time, the inductor will be shorted. Okay, so after a very long time, the inductor will be shorted. And now we can do basic analysis to the current at the inductor, which is will be the same current na mo-flow sa atuang 6 ohm. Okay, the same current that will flow in our 6 ohm. Okay, so we will just be doing well, let's redraw na lang para makita niyo. So yeah, 40. This is your 6 ohm. This is your 2 ohm. This is our 4 ohm. This is 40 volts. This is 10 volts. Okay. So, pila ka ang current ni 6 ohm? You can do KVL or mesh. KVL at I2 is the inductor current. KVL at mesh 1. Have negative 40 plus 4I1 plus 2I1 minus I2 plus 10 equal to 0. We'll have 30, negative 30. We have plus 6I1 minus 2I2 equal to 0. So I1 minus 2I2 equal to 30. Okay, that's your equation 1. KVL at mesh 2. We have negative 10 plus 2I2 minus I1 plus 6I2 equal to 0. So we have negative 2I1 plus 8I2 is equal to 10. We find the value of our I1 and I2. Okay, so I1 is equal to 5 over 11. I2 is equal to 30 over 11. Okay. So I2 is our ISS. Okay. So this is our ISS. Now, what we're going to do is we put ISS right here. It's just to I of T is equal to A e to the negative r over L t plus 30 over 11. Now, for our initial condition, so we cannot use 0 because this time frame is no longer 0, no? This circuit configuration and this equation does not belong to 0. It only belongs to greater than 4 seconds. So what we will do is, at the time of the switching action, no, since we know that the inductor resists the change in current, so current at 4 minus, so before the switching action, we have 4 minus. So we will go back here to our equation, no? I at 4 minus is negative 4 e to the negative, how much is our r? R is 10 over 5 t plus 4. Okay. So we will put I at 4 minus, that is also equal to I at 4 plus, that is equal to, this one becomes 4. Okay, this is 4. How much is that? You have negative 4 e to the negative 10 over, that's 2. 2 times 4 times 4 plus 4. So we got 3.99998. So we can see, I guess we can check if 2 times 5. Our tau is L over R, right? L over R, which is 5 over 10. So times 5, that's around 2.5 seconds. So 5 tau is 2.5 seconds. So most probably at 4 seconds, the circuit from above has already achieved the steady state, no? So at 4 minus, the inductor has already achieved a 3.998 ampere for the current. Okay, so we'll just use that 4 minus or 4 plus. Okay, so and we will use that here. Okay, I at 4 minus, I at 4 plus, because it's already on the switching time, a e to the negative. Okay, we have a different r right here. Our r is, how much is our r? We will do the Thevenin. Okay, we will open the inductor. Open the inductor and short the independent sources. Now, we will get a 4 inverse plus 2 inverse of that plus 4 plus 6. 7.33. 7.33 over 5t, which is 4. 5t is 4. I mean t is equal to 4 seconds plus 30 over 11. Okay, how much is this? I at 4 plus is 3.998. Okay. So with that, A is equal to 3.998 minus 30 over 11 divided by e to the negative 7.5 times 4. So 2.833 times 10 to the negative 3. 3.998 11 divided by 833 448. Guess that's too big. Okay, sorry class, no, my mistake. So this one is our equation, no, at the start of the switching at t is equal t greater than 4 seconds. But at the time of the switching action, we are actually considering this as the first time for this equation, no? So as the first time, but at our first equation right here, no, we are using 4 seconds. But at this moment, where we are getting the initial condition, so the initial condition for this circuit is it actually started at 0, no? So we will be considering the 4 seconds as 0 for this kind of circuit. So this one is 0. Because it didn't start at 4 seconds in this time. This circuit started as the time frame is 0. So we will have 0 right here and we will get so A will be 3.998 minus 30 over 11 is 1.2707. Okay, so that is our I of t is equal to okay. So, para dili na lang ta malibog class, we will be using the singularity function. Okay? Singularity function. So, this one will be at t minus 4. Yes. T minus 4. Correct. So, we will be applying this. So, at t minus 4, so I at 4 minus 4 will be 0. E to the negative 7.33 over 5, 4 minus 4, plus 30 over 11. That should be equal to 3.998. So, I at t minus 4 will get a 3.998 8 minus 30 over 11 divided by 1. This should be 8. Is equal to 1.2707. So I add t minus 4 is equal to 1.2707 e to the negative 7.33 over 5 t minus 4 plus 30 over 11. So yeah, this is it. This is the answer. Sorry, I forgot regarding this one. Kindly take note, class, para dili mo masayop next time. Okay, let's go back to the problem. Okay, calculate I for t greater than 0. Okay, we already did that. We have two equations. I of t for 0 to 4 seconds and I of t for t greater than 4 seconds. Now we're going to calculate I for 2 seconds and 5 seconds. So for 2 seconds, we will be using this equation. So I at 2 seconds, kay pasok man siya dara, negative 4e to the negative, so 10, that's 2t, 2 times 2 plus 4. So e to the negative 4e, negative 4. E, I at 2 seconds is equal to 3.926 amps. Okay. And for I at 5 seconds, two 707 e to the negative 7.33 over 5. 5 minus 4 plus 30 over 11. That is equal to. Okay, so I at 5 seconds is equal to 3.0206 ampere. So that's it. Okay, so to summarize our answer, I at t is equal to 0 at time less than 0. We have negative 4e, negative 4e to the negative 2t plus 4 or 0 or okay, seconds. And then we have 1.2707 e negative 7.33 over 5 t minus 4, which is a plus 30 over 11 at t greater than 4 seconds. Okay, so this is our first order differential equations or general solutions with initial conditions and analysis. Okay, let's have another example now. And this one will be on the second order differential equation. So you have the problem right here. Find V of t for t greater than 0 in the RLC circuit of figure 8.50. So we can check the circuit. We have a 40 volts supply. And then we have parallel capacitor and resistor of 50 ohm with a 0.4 Henry inductor and a 30 ohm resistor, but at time less than 0, okay, at time less than 0, the circuit is still complete, no? At time t greater than 0, the supply will be cut off. So we have that to work on, okay? So what we will do is that, okay, we will redraw the circuit and based on the timeline, okay? So let's have this, let's cut off some parts. It's not too big there. So at time less than 0, the circuit would look like this. 40 volts. Then we have a capacitor. Fifty ohm, 0.4 Henry, 30 ohm. So we have here a non-series, non-parallel, no? RLC circuit with a 40 volt supply at time less than 0. So what we will need to do is we will need to get the general formula for this one. So the general equation for this is we're going to get the V of t. There we have V of transient plus VSS. Okay. And since we have a non-parallel, non-series, okay, so we can't use the previous formulas that we have solved for. So we will need to solve it, this one on its own. But solving this one, we can do is that we just need to turn off the 40 volts first, no? 40 volts so that we will learn the transient response. And then later we will determine the VSS. Okay, so turn it off first. So we will have 0.4, then we have 30 ohms. Or actually, we can do this one, no? But since the problem is, okay, let's just ano na lang, padayon lang nato ni. But actually, it's not, this one is not necessary, no? Because we can consider the capacitor and inductor to be already on the steady state. So we will just need to determine the current and the voltage of the capacitor for our initial value. Anyway, just to show you how about let's just do the problem first and then let's show that one later. Let's do the problem first para dili kayo malibog. Let's erase it. Okay, let's do the problem. Okay, find V of t. So we will just need to know the initial conditions of this. So having said that the switching happened at t is equal to 0, we can assume that the current, the IL and VC has reached steady state. Assume that the IL and VC has reached steady state. So redrawing it in its steady state form, redraw in its steady state form. So this is the 30 ohm. Our inductor will be shorted. We have 50 ohm. And we have an open capacitor. We have an open capacitor. Okay. We have our I right here and our VC right here. So VC is equal to 40 times 50 divided by 18. So that will be, that will be 25. Okay, that's for your VC, and then for your IL, or let's just say this is VO, this is IO, since it will be the initial condition for the next timeline. So we have a different direction now, but IO, since this one is open, will just be 40 divided by 80. It's equal to 0.5, and we will have to put a negative value for that. Okay, so negative because this formula is based on passive sign, and we know that the current is going out of the 40 volts supply. So your IL is the negative of that amps and volts. Okay. So now this is RVO and IO. Let's do the steady state form T less than 0. At T greater than 0, our supply will be cut off and we're left with a parallel RLC circuit. Okay. 0.4 20 microfarad. Okay, so we already solved parallel source free, and we'll just copy that V of t. V of t is equal to d squared V over dt squared plus what is that? So 1 over RC dV dt plus V over LC. So this is the differential equation. This is the differential equation for the source-free parallel RLC circuit. We'll have to solve for its values. Okay. The R is equal to 50. L is equal to 0.4. And C is equal to 20 microfarad. So we will need to solve for its solution, okay, based on the one that we did last time. So you can just go directly to the to this one, S square plus 1 over RC S plus 1 over LC equal to 0 using quadratic formula. S is equal to negative 1 over RC plus minus square root of B squared, that's 1 over RC square minus 4 times 1 times 1 over LC. Over 2. So S1 and 2 is equal to negative 1 over 2 RC plus minus square root of 1 over 2 RC square. Cancel out ang 4. And the 2 enters the quadratic formula. We are left with 1 over square root of LC square. Alpha is equal to 1 over 2 RC. Mega sub O is equal to 1 over square root of LC. Now you need to check which one is bigger, the alpha or the omega sub O. So alpha is equal to 1 over 2 times 50 times 20 microfarad. So let's solve that one. So this one we will get a value of 500. Omega sub O is equal to 1 over square root of LC. That is equal to 1 over square root of 2.4 times 20 microfarad is equal to 1 over square root of 1 times 300. So alpha is greater than omega sub O. So we have an overdamp. So overdamp, the circuit is overdamp. Meaning our solution will be V of t is equal to A1 t to the S1t plus A2 to the S2 t plus VSS. So VSS right here, we will not be using it because there's no steady state. The the steady state of this one is 0 since we are source free. Okay. So after a very long time, everything comes to 0. So 0 ang VSS na to dari. Okay, moving on, we will need to determine the initial condition so that we can get the values of our A1 and our A2. Okay, so what are the conditions that we have? We have IO and VO. So since we are doing VO, let's start with this one. V at 0 is equal to A1. Wait. So we will need to determine the SDI first so that we can get that out of the way. S is equal to, let's just solve this one. Using the formula, quadratic formula. So we have here negative 853.556. And the other one is we have negative 146.44. Okay, so with that, we will have V of t is equal to A1 e to the negative 146.443 t plus A2 e negative 853.556 t plus VSS is 0. Now we will do V at 0 is equal to, sila man natong V at 0. Let's go here. We have an initial state of 25 volts. That's 25. Is equal to A1 e to the negative e to the 0. So that's A1 plus A2. 0 na so A1 plus A2. Okay. We have equation 1. Okay. Equation 1, but we have two unknowns. So we need two equations. So where can we get the other equation? We get the other equation by deriving this. Okay. We will need to derive dV for dt is equal to negative 146.443 A1 e to the negative 146.333 minus 853.556 8 e to the negative 853.556 t. Now, we have this derivative. We will need to find the dv at 0 over dt. So, this one will become 0, 0. So, we will get negative 146.443 A1 plus minus 853.55682. But how much is this one? Okay, so we have not yet get the answer for this. This is part of the initial conditions, no, that we need to be solving. Okay, so there are you can get four equations from this. Okay? So first is, let me discuss, okay? Let me discuss it right here. Let's just put a red mark. Okay. Initial conditions. First derivative. dvo over dt and dv dio over dt. So we can actually get it from our, let's see, from IC is equal to C dv dt, where we can transpose this one. We'll be getting dvo over dt is equal to IO over the capacitance. Okay, so this is one. Another one, number 2, is we can get it from VL is equal to L di dt, where dio over dt is equal to VO initial condition over N. Okay, that's one. We can also get it, number 3, is from our series loop, no? If you have a series circuit, diba, we will get RI, KVL, RI plus VL plus VC is equal to 0. This is for series RLC. So from series RLC, we will have this condition right here. So RI, so we will need to change this one into currents. RI plus LDI dt plus, since the capacitor current and inductor current is the same, so this one will become 1 over C integral of I L dt equal to 0, or wait, let me check. Okay, so we will have so since this is an RLC circuit, we both have initial value mo po di ay sa VO. So we will have this as VO, and then we will have this as R IO plus L D I O dt plus VO to 0. So there we can get a DIO dt is equal to negative RIO minus VO divided by M. So this is third. And for the fourth, we have parallel RLC. We will get PCL IR plus IL plus IC. So there we will change this into voltage. They all have the same voltage since they're parallel. So V over R plus IL is equal to IO, that's the initial condition, and IC is equal to CdV 0 dt. So we will get dV at 0 dt is equal to negative VO over R minus IO divided by C. Okay, so these are the four initial conditions that we are able to use for the differential equation na derivative value. So we will be checking which one applies to our circuit. So going back to our problem, no? Okay, we have dVO over dt. So I guess we can use this one since our circuit is parallel RLC. We can use this one right here. dVO is equal to dVO over dt is equal to Okay, so we can see, class, that this number 4 is the most applicable initial condition. Why? Because we are using the dVO first. Okay, so that's one thing. But compare it to the dVO right here. I think this is actually wrong. This one should not be O, but this one is IC. IC. But we don't know the IC, right? We don't know the IC at this part. And this one also, this is VN. The VN. We also don't know that one. So Looking at the other components, I guess we have all the components. Then we can apply it. Okay. So we have VO over R. That's the initial condition of our capacitor. VO over R negative minus IO over C. Okay, so substituting 25 negative minus R is 50. R is 50 minus, we have IO and C, the microfarad and negative 0.5 amperes. 20 microfarad and negative 0.5. Okay, so our dVO over dt is equal to solving for this one, we get 0.5, and then this one becomes positive, so we get a dVO of 0. Okay, so this one will just be equal to 0. So there we have a second equation, negative 146.443 V1 plus 853.5562 or to 0. That is our second equation. Okay, solving for the two equations, we can just write it like this. Negative 146.443 minus 853.556 0 square B1 B2 is equal to 0. The other one is 1, 1, and 20. 1, 1, and 2. So A1 is equal to A2 is equal to A1 is equal to 30.177. A2 is equal to negative 5.177. Okay, so this is our final answer now. So we translate this one here. C. And so this one is 0. We have 0 steady state. P of t is equal to 30.177 e to the negative 146.443t minus 5.177 e to the negative 853.5560. Okay, so this is the V of t, no, for t greater than 0. Let's go back to the question. So that is how we solve second order differential equation with its analysis and the initial conditions. So this one would be different, no, if, like for example, the first one that we did is if the initial condition is not actually the steady state. Okay? So it would be the same in our first example. In the first order, where we will need to get the general equation for a time less than 0. And then we will have to transpose the time at t greater than 0. So this, so this is this one. Let's have another example. Okay. Where we will be getting the I of t and IR of t for t greater than 0. Okay, once again, we have here second order differential equation circuit, and it has more things that are happening in here. There's a switching, and we have here a unit step function. So we will need to incorporate that in our analysis. Okay. So let's go ahead and solve this one. We are going to look for the I of t and the IR of t for t greater than 0. Okay, so before we solve for the t greater than 0, let's solve first what happens at t less than 0. T less than 0, so our circuit would look like something like this. We have our 4 amps. So since this one is open, T equal to 0, okay, so this one was open. So this one was not non-existent. Doesn't exist. Let's erase this. Okay, since this one is open at t less than 0 and then it was short at t greater than 0. So we will have to start here. Okay, and then we have our capacitor right here and another resistor, and we have here 30 U of t. And since that's U of t, it only works at time less than 0. volts, we have 20 ohm. This is our IR. Okay, so what we have here is a step response of an RC circuit. Yes. But since there's no other conditions, it is safe to assume that this setup has been already there for a long time and the capacitor has been charged. Okay. And has reached its steady state. Okay. So we do not need to solve for its general solution. Okay. But we can actually solve for its general solution, but it's not necessary for this kind of problem. Okay, so we will just go ahead and solve for the VO. VO is equal to 30 times 20 over 40. So that would be equal to 15 volts for our VO. Also seeing here that we have 4 amps and a 20 Henry inductor, although this was separated from the circuit, no, but we can actually also solve for the initial condition of our IC. In our IC, IL, initial condition of our inductance current will be 4 amps. Okay. Since there's only 2 of them, so the 4 amps will, there's no way of going anywhere but here in the inductance. Okay, so there we have our initial conditions. Then let's move on to at t greater than 0. And we will redraw our circuit. Now at t greater than 0, the switch will close. And then the 30U of t will be shorted. Okay. So what we have left is the 4 amps with the inductor. And then we have the 20 ohm capacitor, another 20 ohm. Oops. So since we don't have a voltage anymore, let's just go ahead and make a parallel 20 ohm. A millifarad, another 20 ohm, and then this one is a 2000. Okay, so this one is a step response parallel RLC circuit. Okay. So since we're going to solve for the I of t is equal to A. Okay, so not yet, we're not there yet. We need to know the differential equation, which is the complete response. I of t is equal to I transient plus ISS. Okay, I transient so we have here our I. This is our I. I of t is equal to the parallel RLC circuit. Let us check the value of that. Okay, so we have here d square I over dt plus 1 over RC di dt plus I over LC equal to 0. So this is our um, source-free parallel RLC, the second order differential equation. So we're going to determine the equation. No? This is S squared plus 1 over RC plus 1 over RCS plus 1 over LC equal to 0. Then S1, S2 is equal to negative 1 over 2 RC plus minus square root of 1 over 2 RC square minus 1 over square root of LC square. Okay, so this is our alpha is equal to 1 over 2 RC omega sub O is equal to 1 over square root of LC. Now, the value of this is that alpha is equal to 1 over 2. So we have here 1 over 2 times R. R equivalent, since we have 2 parallel 20 ohm, then that is equivalent to 10 ohms. And our capacitor is 8 milli. Okay. 8 milli, that is equal to 6.25. Mega sub O is equal to 1 over square root of 20 times 8 milli. That is equal to 2.5. Okay, so alpha is greater than omega sub O. We have overdamp. So if we have overdamp, I of t is equal to A1 e to the ST A1 is A2 e to the S2 t plus ISS. Okay, ISS, how much is our ISS? If we get into the steady state, this one becomes open. This one, combine the two resistor, that becomes 10. So this becomes shorted. Okay, so when it's shorted, you will still get the 4 amps. So this one is equal to 4 amps still. Okay, next, let's move on to S1, S2. S1 is equal to, based on the formula, and S2 based on the formula. We have negative 6.25 plus square root of square root of 6.25 square minus 2.5 square, that is equal to negative 0.5217. S2 is equal to negative 11.978. Going back here, I of t is equal to A1 e to the S1 A1 negative 0.5217 t plus A2 e to the negative 11.978 t plus 4 amps. Now we will be doing the initial condition I at 0, that is equal to, so I at 0, we get 4 amps. So I at 0 is 4 amps also. And then plus A1 plus A2 4, no, this one is equal to 4 amps. When I at 0. Okay, so we have A1 plus A2 equal to 0. So, cancel out 4. Next, we will be doing the I of t. Di of dt is equal to derivative of this one. Okay, so we will have negative 0.5217 A1 e to the negative 0.5217 t minus 11.978 A2 e to the negative 11.978 t. For when you derive it, it becomes 0. Now we will determine the value of the IO dt. Let's go back to our, looking here, we have parallel, no? So looking back here, we have here a parallel, which is the same as before, no? So we will let's just copy this one. Let's copy that. Okay, there's no more space. Okay, so we have here, and then let's just equate that. And, sorry, it's a different one. Okay, sorry, we need DIO, not DBO. No. So we will not be using this one. Let's go back to our the list for our initial condition. Okay, looking right here, we have the IO right here. Let's copy that. Okay, so this one is your VL, right? Okay, since our at time 0, no? At time 0 is we have a parallel right here. And since the capacitor voltage stays the same at 0 minus, V at 0 minus is equal to V0 plus. So, yes, the capacitor voltage stays the same. And now, at time 0, they are in parallel, meaning the voltage at our inductor is the same as the voltage in our capacitor. So we can just use this one and VL, where VL is equal to RVO. Si VO is the capacitor voltage. Okay, DI0 rather, is equal to our initial voltage VO, which is 15 volts. Okay, we have 15 volts right here, divided by RL is 2000. So now we have 3/4. 3/4. Okay, so there we have, we can substitute it In our equation, let's copy our equation. DIO over dt is equal to 3/4. That is equal to negative 0.5217 A1 T. Oh, this one becomes 0. So this is already 1. E to the 0 is 1. Minus 11.7882. So this is our second equation. And then this one is our first equation. Resolving these two, let's have 1, A1, A2, equal to 0, and we have here negative 0.5217. Negative 11.978, negative 0.517, okay, equal to 3/4. Okay, find the value of your A1, A2. Okay, the answer is 0.0654, negative 0.0654 or 55. Okay, so substituting that in our equation, I of t is equal to 0.0654 e to the negative 0.5217 t minus 0.0654 e to the negative 11.978 t plus 4. Okay. So there we have I of t. Now let's find the value of our Ri. So Ri. Our RIR is just t greater than 0. Okay. We can actually solve for the IR based on the inductor voltage. No? So inductor voltage is VL is equal to L di dt. Okay, so we will just be deriving this one and multiply it by 20 times derivative, which is 0.0654 times negative 0.5217 e to the negative 0.5217 t minus 0.0654 times negative 11.978 e to the negative 11.978 t. Derivative of 4 is 0. So you will get an inductor voltage of negative 0.034 and 1.034 na lang. 0.34 times 20. 0.